Now that you know how to draw line structures in the simplest manner possible, the line angle structures, let's talk about isomers and acids and bases. So let's first cover isomers before we talk about acids and bases. So isomers will have the same chemical formula, but they're going to have different pattern in their structure of arrangement of groups of atoms and or atoms. So for example here you have butane. You learn about this in chapter 3. Butane has 4 carbons and of course it has 10 hydrogens. This molecule right here is called 2-methylpropane. Again, you'll learn the naming, the nomenclature in chapter 3. This one still has 4 carbons, and if you count, you're gonna have 10 hydrogens. But look, the way they're arranged, the way the elements or the atoms are arranged is different. So they have the same chemical formula, but they're gonna have a different pattern in their structural drawing. Now, if I am to draw the line angle structure for butane, it's just gonna be like that, where this will be carbon 1, this will be carbon 2, this will be carbon 3, and this will be carbon 4. The hydrogens are not shown, but to satisfy 8 electrons around each of these numbered carbons, you can tell that you'll need 4 bonds around each of these. So that's how you'll know there are 2 hydrogens here, 2 here, 3 there, and 3 on carbon 1. For this one, the structure will be like this. Now you see how clearly the pattern is, the structures are different. They have the same chemical formula, but different structural formula. This one is ethanol. Again, the line angle formula will be like this. We show the hydrogens that are not attached to to carbon. And then here, this is dimethyl ether. It's gonna take the bent shape of water. So again, the general formula for these two guys is C2H6. Both of them will have 2 carbons and 6 hydrogens. But now their structures is different. In fact, this is an alcohol and that's an ether. We talked about functional groups. You understand that. Now, there's importance of this isomerism property because it's gonna affect the physical properties of these compounds or molecules, so to speak. So propanol, one propanol, to draw it, showing line angle formula, one propanol should probably be drawn like that with 3 carbons and an OH. The boiling point is 97.4 degrees. But 2-propanol, which is the isomer of 1-propanol, okay, has a boiling point of 82. In fact, you should note that branching decreases boiling point and melting point. I said that before. Branching means you have something popping out of the longest carbon chain. Their general formula, of course, is C3. Both of them will have the same structure, same chemical formula, which is C3 H what? Someone count. H8. Both of them is C3H8, but they have different structural formula. So another examples of structural formulas are what you see here. Do not confuse isomers with different way of drawing in different orientations, because all these guys are the same. Because I see on carbon 1 I have 2 hydrogens and a chlorine, on carbon 1 2 hydrogens and a chlorine, on carbon 1 2 hydrogens and a chlorine. They are the same. Carbon 2 2 hydrogens and a chlorine, carbon 2 2 hydrogens and a chlorine, carbon 2 2 hydrogens and a chlorine. So all these guys are the same. These are not structural isomers. These are just conformational. These are called conformation. Different conformations of the same molecule. Okay, they have different conformation, but it's the same molecule. Where chlorine is on the on horizontal, here it's down. You can have it up, you can have it horizontal. It's just the same thing. Same applies with this. All these are the same. Because I see 2 chlorines on carbon 1. and I see 3 hydrogens on carbon 2. So all these drawings are the same. They are not isomers. So be careful not to confuse the same molecule drawn in different conformation orientations. You see, the boiling point for all these will be the same, 83.5 for all these 3. The boiling point for these 3 will be 57.3, which means the same. They have the same degree of boiling point. So to remind you, whenever you are writing an equation of reaction, an arrow that's going to be between the reactants and products simply means that the reactants react to form the products. Whenever you have 2 half arrows pointing on opposite sides, that's an equilibrium. Reaction can go equally forward and backward. And then this one is for resonance. We talked about resonance before. Okay, different representation of the same structure by moving bonds and lone pairs of electrons around. Why do we use arrows in organic chemistry? Unfortunately, that's the language we speak. Like you'd speak English, Spanish, French. Organic chemistry uses arrows. That's how we can explain where electrons are coming from and where they are ending. A double-headed arrow moves 2 electrons. Single-headed arrow, what I call fish hook. Okay, so this is double-ended. Fish hook will move a single electron, and usually it forms radicals. The rules are simple. The tail of the arrow starts from electrons where they are, and the head of the arrow points to where those electrons will end up. For example, let's say you're given the nail polish remover we call acetone, the ketone. It's a ketone. It falls under the functional group ketones. You know, if I am to show the electrons between the carbon here and the oxygen, I have to show 4 of them because 2 electrons make 1 bond. Of this double bond, one is going to be a sigma bond, the other one is a pi. Remember, I told you sigma is formed by head-head overlap of orbital. Pi bond is formed by side-side overlap. So in that case, the pi bond is weaker than the sigma. So we use a double-ended arrow to move 2 of these electrons towards the oxygen. Remember, there are 2 lone pairs here. We usually just don't show them unless you are asked to draw the Lewis structure or show all electrons. So the arrow is pushed towards the more electronegative element. In your periodic table, the row that contains carbon, nitrogen, oxygen, I think, and fluorine will have CNOF. Might be, I think it's the second row. Electronegativity increases across the periodic table to your right and upwards. So which means oxygen is more electronegative than carbon. What is electronegativity? If you forgot, I told you in an earlier lecture that electronegativity is the affinity of an element for affinity of an atom of an element for electrons. Like that atom really wants to grab electrons. As you go towards the right, fluorine will really want to hold on electrons tighter than carbon, oxygen, or nitrogen because it's farthest to the right of the periodic table. We don't consider the group 8 elements because those don't gain, don't lose. So in this case, I'm emphasizing electronegativity because that's going to guide you to know where the electrons are going. Usually electrons go from a region where they are more to a region where they are needed. So oxygen being more electronegative than the carbon here, than the carbon there, okay, it's going to want to take those electrons. So we push electrons towards the oxygen and not the other way around. So doing so, you are stealing 1 valent electron from this carbon right here. Because remember, carbon has a valency of 4 and it uses those 4, right? Carbon has a valency of 4. So it uses these 4 to bond, but now you're moving 2 electrons. One of the electron belongs to oxygen, the other one belongs to carbon to make up a bond, right? So if you're moving 2 electrons to oxygen, you're denying this carbon 1 electron. So it's now left with 3 electrons. So in that case, this carbon is going to be positive, meaning you need to add back its electron for the carbon to be octet. The oxygen right now is gonna have, so for the case of oxygen had okay, so if you are to consider the valency of oxygen will be 1, 2, 3, 4, 5, 6, will be 6. But the moment you move 2 electrons towards the oxygen, it comes with an extra 1 electron. So the valency becomes 7. Okay, so that's why we have a negative charge here. There's 1 more electron. In other words, one can still use the formal charge calculation, where formal charge equals to number of valent electrons in a free atom. For example, carbon, the valency is 4. There's no lone pair on the carbon, so 0. How many bonds? 3, so minus 3. I'm getting plus 1. That's where the plus came from. The oxygen, the formal charge of the oxygen, the valency of oxygen in the periodic table is 6. It's on main group 6. And then if you look carefully, since oxygen had 2 lone pairs and you just broke the bond and gave those 2 electrons to oxygen, so the oxygen will have 6 electrons, okay, on the outside, or 3 lone pairs, and then there's 1 bond to it, so you get -1. So that's where the -1 could come from. You either gonna reason this way or you're gonna do the FC calculations. So that arrow right here shows resonance. Like this structure can give that structure, and this structure you can do the reverse, because now you're pushing towards the carbon because there's less electron density here. Like I said, you push the electrons towards the side where they're needed. If there's a positive sign, the electrons are lacking there. Remember here, oxygen is partially negative, so it will want those electrons in this state. Okay, but okay, so you do the calculations, you can get a formal charge. And if you want to go back, you can neutralize the positive formal charge by donating the electrons back to get this double bond. And that's what's being done here. You just simply move 1 lone pair back. It gives you back the acetone that you started with. Okay, so the reverse process could be possible for this one, of course. So that's an illustration of where an equilibrium arrow can be used and where resonances can be applied.